Okay, to finish up chapter 15, we're going to take a look at indicators, which are substances that change colors in different pH solutions. Now, different indicators change pH at different regions, so it depends on what our solution is, but we're looking for color changes at equivalence points, which we now know are not always at 7. So here's a couple examples of some indicators. Here's a strong acid and a strong base. Now this one has a pH of 7 at the equivalence point. So we can see that the range here that this changes at the equivalence point with just a drop there, both of these indicators are going to change in the steepest part of this graph. So actually when we use phenolphthalein, phenolphthalein is not exactly at 7 that the color change happens, but that drop jumps the pH so rapidly in this range that we're able to use phenolphthalein without much problem. It's a good way to show where the equivalence point is visually. But methyl red is also a good one for this particular problem because it changes down here at 4 and it jumps all the way up to like the mid-6 range. But if we looked at this one over here, where the equivalence point is above 7, that's where we have a weak acid plus a strong base, because there's the NaOH being titrated. It makes water, and it makes a conjugate. So the conjugate is still present at the equivalence point. Now my equivalence point is above 7, it's 8 point something in there. And you can see that methyl red doesn't work because the steepest part of this graph is now out of the range of methyl red. So we want to find indicators that change color around our equivalence point. For weak acids, it's going to be above 7. For weak bases, it's probably going to be down below 7. And then strong acids and bases are the ones that are right at 7. So every indicator has different color ranges in different spots. And depending on what your needs are, you just need to pick a suitable indicator. So a 1 liter solution of 0.1 molar ammonia is used to titrated with hydrochloric acid. Select a suitable indicator. Well, this question is really asking for the pH at the equivalence point, and then we just find an indicator that will work. So what we need to do here is set up a neutralization reaction between the acid and the ammonia to make NH3, because that's going to be, NH4 plus. That'll give us the equivalence point. So 1 liter of a 0.1 molar ammonia solution gives me 0.1 moles. This is going to be a reaction, and everything is in moles. So at the equivalence point, we know we need 0.1 moles of acid. So setting this first part up is pretty straightforward. We just need to know what equivalence point means. Okay, so here we have a conjugate acid at the equivalence point. We need to know what the pH of that is. To do that, we need to find the volume so that we can divide the moles per liter. Now this acid here, this 0.1 moles, is going to be a clue for the volume because we know that we have 0.1 moles of acid and it is a 0.2 molar solution. So 0.2 moles per liter. We have to pause. They didn't give us a volume. We have to pause and find out that this is half a liter of acid. We add that half a liter into the original 1 liter of the ammonia, and we get a 1.5 liter solution. So my ammonia is going to be 0.0667 molar. Okay, so we need an equilibrium problem for that. That is my NH4 plus is going to dissociate into H plus and NH3, and that is a 0.0667 molar solution. Minus X These start out at 0 because the way we're gone, and we're going to make some more. We get x and an x squared over 0.0677 minus x equals the Ka, 5.6 times 10 to the negative 10th. Okay, so that will give me my x value and my pH. X is going to come out to be 6.11. Oop. Switch tools. 6.11 times 10 to the negative 6th for a pH. Negative log of that equals 5.21. Okay, so that's the first part of the problem. What is the pH? But the question is really asking for what is a suitable indicator. So we need to go over to our chart on the other slides and figure out what the best indicator is. We want something that changes colors around 5.21, that has a really clear color change, and it looks like the best one in this case is going to be methyl red. Okay. We're used to picking phenolphthalein for things, but it doesn't always work out to be the best option. Different solutions change pHs at different colors. This one we need something that changes at 5.21. Now we can use that chart for other purposes too, to see when picking indicators what color they will be under certain conditions to see if we can predict them. A solution has a pH of 7. What will the color of the solutions be at a pH of 7? The following indicators. We've got phenolphthalein, methyl orange, brome thymol blue, and thymol blue. Let's take another look at the chart. The first one we're going to do is phenolphthalein. Now at a pH of 7, we're pretty familiar with that. We think that's when it's pink, but recall that that is when the phenolphthalein is actually clear. It changes, we said a little bit ago, it actually doesn't change until a pH of like 8 or 9. So it'll be clear at a pH of 7, but the titration curve changes so quickly at there that it's pretty close. That light pink color is close to the end point anyway. The end point and equivalence point are technically different. The end point is a titration visual thing, where the equivalence point is more of a mathematical thing. But in any case, they overlap a lot. Brome thymol blue, pH 7, that's going to be right here. That one looks like it's going to be green. Oh, I skipped methyl orange. There's the brome thymol blue that we did. Methyl orange, not actually on this chart. Interesting. Let's just skip that one and go to thymol blue. So thymol blue, pH is 7 here. It's actually between two colors, but remember these are they just tell us where they change. That color actually extends kind of both directions until the end of the curve, or it hits another one. So this one looks like it's diprotic, but this is yellow here, and that yellow color, if we were to color it in, actually extends from here to here. So from the pH of 3 all the way to 8, that brome thymol blue is actually yellow. So the color change won't happen to make that green color until 8.5. But right here it is still going to be yellow, so it's going to continue on, which is why that phenolphthalein, it's on the clear side, so we say it's clear all the way down to a pH of 0, and it's pink all the way up to a pH of 14. That's how we read this graph. So which indicator would be the most suitable for each titration? So we look for color changes at or near the equivalence point, and the indicators give us the end point. So in A, my chart changes so steeply from here to here that it actually looks like all three of them are going to be okay. Whereas in B, my chart changes, my equivalence point jump is actually in that range. So methyl red is not going to work for that one, but it looks like the other two are going to be okay. Where in C, the equivalence point is below 7, so phenolphthalein actually would be a bad one in this case. But the brome thymol blue and methyl red will both be good choices. So we just need to understand which titrations will change pHs at 7, below 7, above 7, and how to kind of figure out which colors they all are.